Hello, everyone. Thanks for coming. I'm Martin Gordon. I work at Developer Relations in Google. And today I have with me Thomas Park.
I'm a software engineer at Google. I work out of the Seattle office on Google Cloud Platform.
You're a software engineer?
I am.
With a jacket?
Well, you know.
All right. That also exists. So Thomas is working on this product. He will show you a live demo later. But I would like to spend most of the time with you going through the actual workings, the actual algorithm of Cloud Dataflow. So let's jump right in. Cloud Dataflow is...
Oh, sorry.
And you might want to activate caffeine on there. No, you don't have it? Oh,
no,
right.
I don't.
So Cloud Dataflow is a tool for crunching data. We have been challenged. Google has published the MapReduce paper 10 years ago, and a lot of time has elapsed since. As you can imagine, the technology has moved forward. So we've been challenged in the past for not having a MapReduce as a service. The product that we have announced at last Google I/O, Cloud Dataflow, is, you can call it a MapReduce as a service, but it's much more than MapReduce. The paradigm is different, it's much more powerful. Let's try to see what it does with an example. So here is something I might want to do. I want to autocomplete hashtags. The same thing as the browser does when you start typing, it has autocompletions, but I only want to do it with hashtags. My input data, tweets. My output data, the autocomplete predictions. What do I need to do? Well, I need to read the tweets. I need to extract the hashtags from the tweets. I need to count them to find the most popular hashtags. And then, from those hashtags, I will compute prefixes. So Argentina becomes A, AR, ARG, all the prefixes in Argentina. And then the last step is to take all those prefixes and, for a given prefix, find out what are the 3 most frequent completions, hashtags, which will become the top completions for that prefix. So if I type A, if I type AR, if I type ARG, I have different completions based on their frequency. Now, if you look at this execution, how many of you have already used MapReduce in production or to play with data? Okay, quite a few. So among those, looking at this graph, can you tell me how many MapReduces I'm running here? A number? Okay, it's not so easy. It's 2 MapReduces. Now, if I was actually running this on top of MapReduce, I would have to instantiate my first MapReduce cluster, my second MapReduce cluster, shuffle the data between them, take care of the intermediate values. As a data scientist, that's not fun. That's not what I want to do. This is what I want to do. I have high-level constructs in my favorite language, which happens to be, well, we are at Devox. What's your favorite language? Java, yeah. Python, thank you. Nobody said JavaScript, thank you for that. I can allow myself this joke. I had a talk on front-end and Polymer before, so people know that I'm okay with JavaScript. So here is the high-level code that you would use to execute this. And the core of it, apart from reading and writing the data, is that you process it using those primitives. One primitive is parallel do with a function that does something. The new extract tags is a class that has a do function that actually does what you want to do on your tags. Count, which is an aggregation function. Parallel do again, which does the expanding of prefixes, the bit that from Argentina extracts A and AR and ARG and so on. And then top, which is another aggregation function. So that's the promise here. The promise is that this is, as a data scientist, the code you are going to write. And from this, Dataflow can infer the actual execution graph, which is made of possibly several MapReduces combined in various ways, and it will also deploy that execution graph on actual machines and run it. And then if you want to change anything, instead of changing your cluster topology by hand and redeploying stuff in different ways and redoing your networking, you change the code here and hit enter, and that deploys a new cluster that does your new thing. How does it work? Well, before we dive into the exact workings, I have to explain to you how MapReduce works. Because in the title, nobody uses MapReduce. Of course, I lied. We do use MapReduce, but it's a building block of a bigger thing. So, MapReduce. MapReduce is like making sandwiches. You have ingredients. You do a map step that does stuff on those ingredients. They become processed ingredients. And then you have a shuffle and reduce step that puts those ingredients into sandwiches. Clear for everyone? There is a mathematician in the first row that should be shouting, "This is not mathematical enough." Okay, I get it. Let's try to put it with a little bit more form. So you have data. You define a map function, so that is your code, whatever it does, that filters and transforms this data. Actually, the output is not transformed data. The output is usually key-value pairs. So you do stuff to your data, but you also assign a key to each piece of data. Here, for example, my keys are red and blue. Then the shuffle step is about grouping similar keys together. And then the reduce step is about taking those data that have the same key and applying some reduce function that, again, you supplied. And these are the machines. The graph is maybe a little bit more too theoretical, but these are the actual computers this is working on. And M on R are two functions I have supplied, Java functions, which have been shipped to those remote machines for execution using this MapReduce cluster topology. Okay, what is this for? Well, it was invented at Google, so it wouldn't be useful for anything if it couldn't do web indexing. Typical example, you have the web pages. The mappers will take the web page, extract keywords. So the output here is a keyword and a URL. Then you put all the similar keywords together with their URLs, and the reduce step actually writes the index from this. Okay, so now you know what MapReduce is, but that's not all. There is actually something magical that happens when the reduce step is associative. Again, I do my mapping, and I have my key-value pairs process data with red and blue as keys. But now, if the reduce step is associative, it's an addition, for example, those mappers, they can already sort my elements by keys, put all the similar keys together, and start adding them. So here, I can actually ship the reduce code into mapper nodes, and they can start computing partial sums, because sum is associative, so I can compute partial sums and reapply the reduce function and reapply it again on later results. And then the shuffle step just shuffles the intermediate results. Benefit here, those are aggregated results, already aggregated results. So here there's very little traffic on the network. Those results are already partial sums. And at the end, my final reduce simply finishes the last sums. And usually one reduce node will do if I have to add 20 numbers from my 20 mappers. So we'll see this again and again. In MapReduce, when the reduce step is associative, you can ship the reduce code up into mapper nodes, and magic happens. You have much less traffic on your network, and it's much more efficient. Example, again, these are your machines. Typical example, counting stuff. So let's say I'm counting people, and I have a file with the world population in it. I want to count all Brazilian and all Chinese. So map, I take the data. If the guy is either Brazilian or Chinese, I output 1. But I'm just summing them, in the mappers. I can already do the partial sums and say on this mapper, now I have 3 Chinese and 3 Brazilians. So the next mapper, I have 3 Chinese and 4 Brazilians, and so on. My shuffle step, it's just these intermediate sums that get shuffled to the reduced machines, which completes the sum. And for those who are following, there is apparently a summing mistake in this slide. Someone reported that to me. 6, 8, 7, and 3 is 10 and not 9. Indeed, I'll fix it. All right, so this is MapReduce. This was published in 2004. It's been 10 years. Today, if you want to work with big data, we have been publishing lots of big data papers along those years. I won't go through all of them. One that I want to mention is Dremel, which is known as BigQuery today. There are people running SQL syntax on top of MapReduce. Actually, we have this product that is specialized in only running SQL queries on top of very, very big databases for your analytics needs. So if your problem can be expressed as a SQL query over a big database, don't even think about MapReduce or Dataflow or anything. Jump straight into BigQuery. BigQuery is a completely hosted service. You upload your data, you type your query, 10 seconds later you have your result. And the service has spun up 300 machines during those 10 seconds. That's fine. At Google, that's fine. And the one paper that I want to talk about today is Flume Java, which is actually the basis for Dataflow. So this you will need if what you want to do with your data exceeds the box of simple MapReduce or exceeds the box of what you can do with a SQL query. And it's pretty generic, so here really you shouldn't have any limitations. MillWheel, just quickly, I will not talk about this. MillWheel is about the networking nitty-gritty of how to get your data flowing reliably in this complex cluster so to make sure that a piece of data leaves a cluster once and once only and arrives to a cluster to another piece of another machine once and once only. So Flume Java. Let's go back to our MapReduce. In Flume Java, you will use high-level primitives, and the map stage will be called parallel do. The shuffle stage will be called group by key, and the reduce stage is actually another parallel do. There are no differences between those two. They work on parallel collections, and if you look here at the intermediate stage, after group by key, I have a collection that here happens to have 2 elements, which are groups of elements with the same key. So that's a parallel connection. Parallel do does something on it in the same way as parallel do does something on the initial data. In the associative case, well, the last parallel do, we call it combined values. It's still a parallel do. It can still be treated as a parallel do, but we give it another name to record the fact that it is associative, because I hope you get this by now. When the reduce step is associative, magic happens. So let's be a little bit more precise. In Flume Java, you have 4 primitives. First, before we go into the primitives, you work on P collections. All of your data is represented in a P collection, a parallel collection. That is an immutable collection that, so if you want to process data, you take them from there and you create a new collection for the next step. The parallel do simply takes a P collection and outputs another P collection of elements of a different type. Group by key will take key value pairs and put them in bags by their key. Combined values actually is a parallel do, but to be more precise, it usually takes the output of the group by key. So key value pairs, but there is one key and already all the values associated to that key, and apply an aggregation function on those values that are associated to one key. So the output is a P collection of key value pairs with one key and one value. The input was one key and all the values related to that value. And finally, flatten, that is for mathematical reasons we need it. It's a set union, so you have two bags of elements of the same type. You put them in one bag. We need it in our graph to be able to put data together. Oops. Okay. Now, we also have derived functions, like count. In the Flume Java, you actually can do just count. But count is implemented using those low-level primitives. Let's see how. And just a warning, P collection of a pair of key value. From now on, I will be calling it P table of key value. Okay, it's too long to write P collection of pair. If it is P collection of a pair of key values, I call it P table. So the parallel do takes an element, and for that value of an element, it outputs 1. That's what counting is. You first say, I have seen one of those. Group by key starts with a P table of T and 1s, so a bag of key value pairs where the key is the value of your element and the value is 1, and it puts all the ones related to one value together. So you end up with a P table of the value of your element and a collection of ones which represents how many of those you had. And the combined values is actually just a sum, so it sums all those ones together. The point here is you can do a count by key using those primitives. A little bit more challenging. Let's do a join. What is a join? So I have one bag of key value pairs of a certain types of values, another bag of key value pairs of another type of values. I want to do a join, which means that I want a single bag that for each key has all the V values for it and all the W values for it. Okay, how do I do that? I should just be able to put those two collections in one bag. But that's not so easy. You can't put them in the same bag. Those elements are not of the same type. So let's make them of the same type. Yeah, this is faking, but let's make them of the same type. We use a tagged union, which actually is just a structure that contains either a V or a W and a tag that says which one it is. So our parallel do simply does this type transformation, and hooray, our elements now are all of the same type. I can put them in the same bag, flatten, same bag. Now I do my group by key, and I need a last operation, a last parallel do, to actually get my elements out of those tagged collections and end up with one key, all the V's related to that key, and all the W's related to that key. So again, the join can be implemented using those low-level primitives. And now that I'm using those primitives, what is this for? If you define your computation in Java using those primitives, the system will be capable of lazy execution, which means that none of those computations will actually be executed until you reach a run command. And at that point, it will take all your computation instructions and build a computation graph out of it, a data flow graph. Once we have this graph, we will be able to optimize it. So I will go through the optimization steps. Once it is optimized, we are ready to deploy this on MapReduces in production. Let's take an example. Example here, I'm on a shopping website, and the marketing guy asked me for a report on shopping sessions. He wants to know for every session how many pages have been visited, if the guy clicked on checkout, and if he clicked on checkout, did he actually pay, was the payment successful? The marketing guys, they like that. So that's my output. Actually, I have a second output, the checkout logs, which are generated by the code of my website. Every time somebody clicks on checkout, I record in the database what he has in his cart and so on. The marketing guy also wants a raw extract of that because he has a nifty visualization tool. All right, I don't want to know, give me the format. I'll give that to you. Now, what do I have as an input? So first, those checkout logs records in my database every time somebody hits checkout with interesting information about what he has in his cart. Then I'm using two payment providers. Okay, so I have payment logs, of course, incompatible, different formats. So I need to transform the first logs using parallel-do-B and the second logs using parallel-do-C before I can put them in one bag and actually apply the transformation I want on them, which is D. And finally, the guy wants to know how many page views in one session, so I'm also inputting my normal website logs and counting the pages related to one session ID. I do a join on the session ID and a final formatting operation F, and that's my output. So forget about what this actually does. I just wanted to tell you that this is a real-world example, and the code I have written using the Flume Java primitives generates this execution graph. Now, what can I do with this graph? Well, the first and pretty obvious thing is that my parallel do's, I can merge them together. Remember what a parallel do is? It's a piece of code that gets shipped to some remote machine for execution. So if I have this piece of code with an output that is consumed by this other piece of code, I can ship both to the remote machine. That will work. There is no problem there. And logically, I call it a new parallel do C plus D. The same actually works for parallel do's. I'm slightly generalizing what my parallel do can do. It can have multiple inputs. Again, this is a piece of code that is shipped to a remote machine. That machine is perfectly allowed to read two files instead of one. That's fine. So in my graph, if I have sibling parallel do's, I can merge them together and create a parallel do that has multiple inputs and multiple outputs. Syncing flattens. Okay, this is totally obvious. The flatten is just a union, okay? So whether I take the output of B and C and put it in a bag now, or if I first apply D and put the results in a bag, that's exactly the same, which means that my flatten can go down. And now, when the flatten is before a group by key, it's not necessary anymore. The group by key operation is a set union. It takes all the inputs and then does the groupings. So this is a completely trivial transformation, but the flatten is not needed there anymore. So two pretty trivial transformations. Now, the non-trivial part. I'm going to do a kind of pattern matching on my graph. And what I want to extract is those patterns, which I called map, shuffle, combine, reduce. So first of all, how do I extract them? I take one group by key, and this is going to be a totally non-mathematical, non-graph theory explanation. I take a group by key, and I pull on it. And all the other group by keys that come with it, I take them with me. So I take groups of group by keys which have a relation by parent. Parallel do's feeding into both. Again, the image, I take a group by key, I pull on it, everything that comes, that is attached to it, comes together. So that gives me my middle column of group by keys. Each of those, the first layer are parallel do's. I will try to find one column of parallel do's before my group by keys. Now, on the output side, to be flexible, if I need the output of a parallel do immediately for another MSRC, I'm allowed to do the direct shortcut that is at the top. But most of the time, I go through a group by key, and after a group by key, I want a combined values, so an associative reduce step, and another parallel do that does something with this output. If I don't have them, no worries. The do nothing combined values is the identity, I just put it there, and the do nothing parallel do is also an identity, I just put it there. But this is the pattern I'm looking for. One column of parallel do's, as many inputs as I want. One column of group by keys, related. And on the output channels, either a straight output or group by key, combined values, and parallel do on the output channel. Now, why do I want to do that? Well, if you look at this group, it's not quite a MapReduce. It's kind of a generalized MapReduce. But it can be executed in exactly the same way as a MapReduce. You have a map step. Okay, it's not defined with one piece of code. It's defined with 3 pieces of code, M1, M2, and 3. Who cares? You know how it is defined. You have a group by key step. Again, it's not just one group by key. There are multiple keys and 2 group by keys. Same thing. You can ship this to your shufflers. That's fine. You know where the data is coming in. You know which keys you are grouping. It works. And on the output as well, you have a combined values. You have a parallel do. Again, you can ship this to your reducers. And this node, which we will call a map shuffle combined reduce, can be executed using the slightly generalized MapReduce framework. Okay, and a last interesting piece of decisions. Let's go back to our autocomplete. We were counting our hashtags, and then there is this expand prefixes step. Well, that one is problematic. It's explosive. For Argentina, it gives me 10 prefixes, A, AR, ARG. It's explosive. So the count on the top, I said, can be broken into their primitives. And now I have an interesting decision to make. Do I group my MSRCs like this? Or do I group them like this? Who has an opinion? All right, this is hard. So, like this, mighty bad idea. Why? The first is a valid MSRC. Okay, I have a parallel do group by key as combined values and another parallel do. But that last parallel do step is explosive. It's multiplying the size of my data by a factor of 8. So I'm actually creating a network, a big network traffic flowing into the second parallel do. That's bad. This is much better. But you will tell me, well, now the network traffic is between the map and the shuffle stage. Why is that better? Someone knows? Associative reduce. Yes, we have this combined value step after the group by key, which means that associative combined values will be shipped into the mapper, and the reductions will start happening in the mapper, so in the E stage. At the output of that, if I put this into an MSRC, at the output of that, I don't have plenty of values. I have already started aggregating them in the mapper. So that fat arrow there is not there anymore if I do this grouping like this. Okay, so a rule of thumb, cut on the thin arrow. Don't cut on the fat arrow. We engineers, we need simple rules of thumb. All right, let's see this in action. So here is again my graph. Flatten, the flattens go down. Oh, sorry. First, count and join. We have seen that they can be replaced by their low-level primitives. Count is a parallel do, group by key, and the actual addition. The join slightly more complicated. The J1s are the creation of the tagged unions. Then you flatten all that, you group them by keys, and you need to unbox them from their tagged unions. All right. So this is the execution graph I'm going to optimize. First, the flatten. It goes down. Down again. Now I have two flattens in front of the group by key. That's useless. The group by key already puts all of its inputs in the same bag. Flatten is just put everything in the same bag. I don't need that. Now my parallel do's. Merge, 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 merge. Oh, here, this merge actually was an interesting decision. I merged it in a certain way. And the last one, merge. I'm just going to move the nodes around. I'm not doing anything at this step at all. Okay? And I'm inserting some identity nodes just so that I can do my pattern matching. Lo and behold, here are my two MapReduces generated from this graph. So in the end, this is what my execution will look like. Two MapReduce steps with 4 inputs and this graph topology. And just to make it real, here are the actual machines that this will be executed on. So I have over there, I have my mappers, I have my reducers, and those are configured with not just one map function, but those are actually configured with my map function A, B, C, D, E, and J1, and the other machines at the end with F and J2, and so on. So here I know exactly how my data flows, I know exactly to which computers I'm shipping my pieces of code. I know how to run this. Performance. Okay, while you have a look on the performance benchmarks, the only takeaway here is that the optimizer, we tested it, it's as good as optimizing by hand. So people who know MapReduce, who know how to arrange them together, they will not do a better job here. And there is an interesting comparison to Sawzall, which is not completely an apples and pears comparison. Sawzall is a DSL for processing logs that we have at Google. So you see that on code size, it's actually very efficient. If your problem is processing logs, the processing can be written in few lines, and Sawzall executes on MapReduce. But the performance is actually crap. And why is that? Well, Sawzall does not have this model of deferred execution where you create a graph, optimize the graph, and all that. And also, it's a high-level language, which means that it doesn't have either any low-level stuff that would allow you to optimize your MapReduces by hand. So you're stuck there. With Flume Java, with Dataflow, we are at the right level of abstraction. It's high level enough to let you do the work you want to do, but it also has these primitives that let the optimizer do the work the optimizer has to do. And now, I'm sure you want to see a live demo, right? Thomas, live demo.
So hi everybody, I'm Thomas Park. I'm a software engineer working on BigQuery actually, but in a prior life I did work on the predecessor to Dataflow. So today I'm going to walk you through an example that I wrote to teach people inside Google how to use the programming primitives. So hopefully it'll be useful for you guys as well. Excuse me. So let's take a quick example. Let's say that you want to extract some data from a set of Apache weblogs. And you can tell that I'm a developer, by the way, because my slides look like crap compared to Martin's. But
that means I'm not a developer? Thank you, Thomas.
No worries. So the timeline in the middle here is basically a graphical representation of a click stream. You have clicks represented as dots, and they proceed over time. So let's say that we wanted to get some information about our weblogs, such as what query terms or what search terms are people using to access our website, and which of those are really sticky. So what query terms actually end up leading to people spending a lot of time on our website. So that might inform our SEO decisions or where we want to monetize the keywords. Excuse me. So here we have clicks with search terms. Now, just getting the search terms out is pretty straightforward. You could do that with grep. But let's say that we want to further our example here by looking at the clicks that were made by different users. So here we have the user in red up top and the user in blue on the bottom. We've separated out their web clicks. Now further, we want to group these clicks into sessions. So we say, I want to get the sessions or the clicks that are within a relatively tight window of time to each other. So this is starting to look a little bit less trivial than just using grep. But we say, okay, these clicks happen relatively close to each other, so we'll count those as one session, and then the user came back later and did a few more clicks, so we'll separate that out into a separate session. Now to blend in the search term information, let's say that we take a look at those sessions that have a search query term in them, like genomics or Dataflow, for example. And we want to roll up the time that was spent in the sessions according to which sessions had these terms in them, and then add that across our entire global user base. So in this example here, we see that we are spending 75 seconds on the site when we came in with the genomic search term, and 100 seconds with Dataflow. So this all of a sudden is looking like a pretty non-trivial bit of code to write. Now, those of you who are experienced MapReduce users might say, okay, so what we can do in this situation is turn to a parallel processing framework such as MapReduce. But the problem with MapReduce is that it's not always obvious exactly how we can decompose the problem into a series of map and reduce operations. Can anybody here tell me in 30 seconds or less what your maps and reduces would look like to generate this? I will buy you a beer. Yeah, it's non-trivial. So one of the really beautiful things about Dataflow is that it lets us work at a higher level of abstraction. In an ideal world, we would start with the algorithm. So my algorithm would look something like this. First, I want to parse the log files. I've got these flat text files. I need to extract meaning from them. Then I need to get the clicks and group them by client. So we can identify individual users by, for example, taking a look at the IP address they came in on and on their user agent, for example. Then we calculate the session times by grouping those clicks that happen within a relatively short period of time to each other. We extract the query terms. So we look at the referrer string and say, aha, this one had a query term in it, so I'll get that information. And then we merge this information together. So we can say, these are the sessions that had query terms, and these are the session times associated with them. Now, I'm not a MapReduce expert. It would take me a little while to figure out how to do this in MapReduce. But the really beautiful thing about Dataflow is that it allows us to think about things in a much more functional manner. So watch this. There's almost a one-to-one, well, actually there is a one-to-one relationship between these steps in the algorithm and things that you would do in Dataflow. Parse log files. Boom. It's a parallel do where you just give it a function that extracts the information from your log files. Awesome. Extract click times, another parallel do that extracts the clicks and then groups them by key, so we get all the clicks from a single user together. Same thing with calculate session times. No problem. Extracting the query terms, exactly the same thing. And then this last one is a little more complicated. Basically, we have to take these two parallel collections and do a co-group by key. One thing I'll note is that Martin has been explaining the Flume Java paper to you. Flume Java has been in use for several years at Google, and so we've learned from some of the operational difficulties with it, so to speak. Flume Java can be very verbose. So the programming primitives that are available in Dataflow are a little bit different. They're actually quite a bit more concise. So having gone from writing Flume Java to writing Dataflow, it's actually a really nice experience. So I think you guys are all going to be pretty excited when you get it. So would anybody like to see this in action? Yeah? All right, let's do it. So I'm going to come. Can everybody read the terminal okay? All right, so what I'm going to do here is start a build. Now, this basically requires that you download the Flume Java, the Dataflow SDK, but it builds with simple Maven commands, so it's pretty easy to embed in your current build environment. I'm going to build a jar file that has all my code and dependencies. There it is. And I'm going to start a quick runner script that I wrote that just executes the jar. So we see this starting up here. It's uploading my jar to Google Cloud Storage. This is so that the worker nodes can get it. Now, this takes a little bit of time to get all fired up. So I'll run you through some other interesting little widgets here while we're looking at it. First, let me take a quick digression. Has anybody here ever heard of Star Wars Kid? Hands? Okay, only a couple of you. So this is a video that went absolutely viral about 10 years ago. I'll just show you a little bit of it. You might be asking yourself, why the hell am I telling you this? I just want to show you this so that when we see the results of the Dataflow pipeline, it makes sense. So Star Wars Kid is basically a video of a high school kid who is spinning the staff around, and somebody remixed it and turned it into this. This is kind of awesome. So it went absolutely off the hook. You see this video on YouTube got almost 30 million views. Now the cool thing about it is that this was originally surfaced on a website called Waxy. This is a blog that basically deals mostly with video games and anime and things like that. But this person decided to open source the weblogs from the time that Star Wars Kid was going absolutely viral. So that's what we're working with here. Let's take a look at this here. So the logs themselves is 1.5 gigs. It's non-trivial. It's almost 10 million lines. It's a fairly chunky amount of data. Here's the compute engine dashboard. This should show us our MapReduce workers, or sorry, our Dataflow workers spinning up.
And first, maybe you should say that the graph is executed on compute engine nodes.
Yeah, thanks for. So what we have here are two different types of nodes. There's worker nodes and there's shuffle nodes. You see we have quite a lot of them here to process this data. So right now your workloads are only constrained by the amount of compute engine quota you have. So you can scale up as much as you need to as long as you have compute engine capacity. And the Dataflow backend will turn this into Dataflow workers and shuffle workers. So let's take a look at the Dataflow UI here. Now this should be our Dataflow. I'm afraid there's been a problem with Dataflow today. For some reason the execution graph is not showing at the moment. What it should look like is something like this. Of course, the program that we're running would have a much more interesting, much more branched out graph, but unfortunately that's not rendering at the moment. But we do see that the logs from your Dataflow execution are persisted in the developer's console, which is pretty cool. Let's go back to our Go back to our terminal for a sec. So we see this is still running. Now, the neat thing about this type of parallel computation is that we are currently running over 1.5 gigs of logs. If we had a terabyte of logs, this should take about the same amount of time to run the computation, assuming that you had enough compute capacity for it. So let's take a look at the code. Here's my session time class. If we look at the main, we see that we have a pipeline that we're building, the pipeline here. And we're applying these, from that pipeline, we get a parallel collection with the input. And then we pass that into this function here, which is calculate session time. So I'll jump into that, and this should look very familiar to all of you. This is basically exactly the same code that I showed you on the previous slide. If we jump into one of these functions here, so calculate functions time, for example, is a pretty simple functor. A lot of you are probably thinking, oh my god, lambdas would be awesome for this, and you're totally right. But basically, calculate session times is just a simple do fun that basically takes some of this data. Oh, in this case, we have to sort it. I think there's a new primitive called key value order by value that will allow us to avoid the sort. But basically, all of these do funs are just really simple snippets of code. And in fact, you can define these inline as anonymous classes. And that works just fine as well. But I'm showing you the entire file here, including imports, copious white space, and comments. We've written this entire program in about 200 lines. If I was taking some shortcuts and defining these things inline, we could probably get this down to about 150. Does anybody have any idea how long this program would be if you wrote it in Hadoop? I don't know either, but I imagine it would be quite a bit longer. All right, let's check back on this guy. A question? Yeah, go for it.
Did you do any benchmark comparing to Spark? Because when I think of verbosity and API which Spark provides seems even better than this one.
Right. So the question is, do we benchmark it against Spark? I actually don't work on the Dataflow team, so I don't have a lot of information about what competitive benchmarkings they've done. But I'd be shocked if there wasn't that data somewhere in Google. But unfortunately, I can't answer that question. So let's see where we're at with this. Aha. So you see now we are tearing down the worker pool, so we should have some results here. Let's take a look. Here's my output directory. And aha, you see now we have our session time data. So what we're looking at here are the click times in milliseconds and the search terms that came in. I apologize, I did not sanitize this data at all, so if there's anything offensive, please forgive me. But what we see is that we can start to see the click times that have a really sticky presence to them, the ones that actually cause the users to stay on the site for a long time. Now, what I'm seeing here, though, is that these results are not sorted. So in MapReduce or in Hadoop, you would have to go and do some kind of potentially nasty hacks to your code to get this to come out sorted. I'm not going to do this in live coding because I'm not a huge fan of live coding. But what I can tell you is that here we have the code right before we write out the results. We have a parallel collection that has the query terms and the search times. All I would have to do to sort this here would be to add another apply step that took the top end. There's primitives in Dataflow that allow you to get the top or the bottom end by key. There's another one forthcoming that can take an arbitrary comparator. So I'd be able to write a comparison function that looked at the value of the key value pair and compared it against and sorted it against other key value pairs rather than looking at just the key. Does that make sense? Great. So let's just jump back here really quick, and we see that I'm now on the default compute engine dashboard. So this means that Dataflow has torn down all my workers. We no longer have anything running. It'll basically start up your MapReduce or start up your Dataflow workers and then tear it down when you're done. So it's very, very simple. And that is it.
No, there's one more thing.
Ah. Let's go back to the slides.
So up to now, we have only spoken about processing files with data. What would it take to process real-time data? And actually, for this hashtag autocomplete feature, that's what you want. You don't want to do the autocomplete on the hashtags that were popular in 2011. You want the hashtags that were popular in the last hour. Dataflow gives you that as well. You have to change your read and write to reading and writing from a stream, and then there is just one line of code that changes. Instead of working on all the data, you work on a time window. And that's it. Now, let's step back and understand what just happened. I changed this one line of code in my processing code. I deployed this, and the processing cluster is doing a completely different thing with actual real-time stuff going on, the data flowing in. It's on autopilot. It can automatically adjust to the volume of the stream that is coming in. And what you did is just one line of code. I think that's the right abstraction layer for data scientists. You don't want to worry about networking and deploying stuff and managing the life cycles of your machines. That's it. Thank you. If you want to tell us something about this session, you have the link there. You can read it. And we still have time for questions. Yes, Samuel.
Okay, just one thing. Do you plan to support Java 8 so you can get rid of all the
The question is, do you plan to support Java 8 so that you can do your do functions using lambdas? That would be a mighty cool idea. I think so. I'm pretty sure this will happen. I don't have an idea of the time frame. And I'm pretty sure it will not happen in the first alpha. Other questions? Yes, please.
Can you run this anywhere else but in Google's cloud?
Well, one place where you can run this, it's on your local machine. That's actually one of the beauties of this. You write the code and it's just Java. You run it on your local machine. It does everything it's supposed to do without you having to instantiate a virtual cluster of MapReduces or whatever on your local machine. So that's one thing.
I'll show you an example really quick, actually. Here's the pipeline that I'm creating in my session time class. To enable this to be unit tested easily, we actually have a test pipeline. So this runs everything in process sequentially, which lets you do things like attach debuggers to it, which is extremely difficult if you're running in a distributed environment and shipping your classes off to remote worker nodes. So you can execute this locally. There's also the ability to execute the pipeline on a single node in a similar manner to this if you don't have large-scale computational needs.
And as to answer your question, can you run this? The goal of Dataflow here is to be a managed service that you provide the code, we take care of the operations for you. So that's a managed service. Now we also publish all of those algorithms. The Flume Java paper is public and so on. So I think the same thing that happened with with MapReduce and Hadoop will happen again. Someone told me that the Apache project that implements Flume, it's called Crunch. I haven't looked it up myself, but you have a specialist over there.
Was there a question over here?
If you're calculating the session times, can you still do it using a sliding window? The sliding window is becoming short.
So the question is, if we calculate the session times, can we do it using a sliding window? Absolutely. The function that I have here, it's just code that you write. So in this situation, calculate session times. This code here gets the click times by client, and then we calculate the session times using this function. So if we jump in here, we see that basically all we're doing is sorting the collection here, and then applying this function, which I'll jump into really quick. And it's pretty straightforward computer science. We're basically just doing an iteration through the clicks that exist. And what I'm doing is saying, if the clicks happened in a short enough period of time to each other, then we count them as part of the same session. Then we add a little bit of time for individual clicks. So you could do whatever you wanted in here. The beauty of it, I'm sorry?
Sliding window will break off.
Mm-hmm.
This period of this array.
Right, but if you have the data available in an array or a list, then you can implement whatever function you want that does calculations on it. You're not convinced? Other questions?
Last question, someone? You have to shout. We don't see you very well. No? All right. Then thank you very much.